Hello everyone, this is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about spanning trees, right? So let's start with a graph. What do you mean by a graph? A graph is nothing but connection of nodes. See, you can call this a connection. All these rounds are my vertices or nodes. You name them A, B, C, D, E. Yeah, this is a graph. Okay, so a graph consists of a set of nodes and a set of vertices. Nodes and edges. Edges are the one which connect these nodes, right? So let's talk about spanning trees. Then what are these spanning trees and how are they connected to a graph, right? Spanning tree is nothing but a subset of nodes in a graph in such a way that it is a tree. The final output is a tree out of a graph and it is a connected one. All nodes are connected. All nodes. So, for example, let's look at the diagram which I have erased by mistake. For example, this is your graph, right? So, what can be a spanning tree for the same? So, it should be a connected one. This is a spanning tree. Why only this one? Let's even this is a spanning tree. These two, this is spanning tree 1 and this is spanning tree 2. Two spanning trees. You can have any number of spanning trees. So a spanning tree does not have cycle and it cannot be a disconnected one. That means you cannot leave a node and say that you cannot something like this. Now here you can see that this node is being removed from the set of the nodes of your graph. So hence this will no longer be called as a spanning tree, right? So spanning trees are collection of edges which connect all the nodes, please remember that all the nodes will be connected in such a way that minimum number of edges will be used. So a disconnected graph does not have any spanning tree and it will not be called as a spanning tree itself, right? So every connected and undirected graph tree has at least one spanning tree. I hope you understand that point. So every connected and undirected one will have a spanning tree, at least one you can expect. Then what do you mean by a minimum spanning tree? A more specialized one, a more deeper I'm talking about. In a connected, please remember these points, in a connected, undirected, in a connected, undirected, weighted. These are the three key points. Please remember, in a connected, undirected, weighted graphs, a spanning tree which is formed in such a way that the sum of the weights on the edges is minimum. The sum of the weights on its edges is minimum is known as a minimum spanning tree. Okay, so what do you mean by this one? Let me explain you in depth. So we have generally graphs. As we said, a graph is a collection of nodes and set of edges, right? So in a graph, we have two types of graphs. Directed, undirected. Two types of graphs we have. And they are further classified into weighted and unweighted. Okay, we can have any combination of that. You can have a directed weighted graph You can have a directed unweighted graph. You can have undirected weighted graph, undirected unweighted graph also. So these are the four combinations of graphs you can have altogether. Okay, minimum spanning tree talks about undirected weighted graphs combination. Okay, undirected weighted graphs combinations. What do you mean by weighted graphs? Weighted graphs mean each and every edge in a graph is going to bear a payload, and that load can be any unit, can be a distance, it can be a number of units you are going to send, the terminology can be anything, the unit can be anything, but it is the payload which the edges are going to bear. Say for example, you can say between, say, distances, you can say from place X, Y, Z. You can travel, the distance between X and Y is 5 kilometers. Then Y to Z is some, say, 6 kilometers. And from X to Z is 10 kilometers. So the the values 5, the numerical values 5, 6, 10 are nothing but weights. Okay, so this is how a weighted graph looks like. So minimum spanning tree is talking about undirected, because if the distance between X and Y is 5 kilometers, from Y to X will also be the same. Is it going to change? It's not going to change. It will be the same 5 kilometers. So it is undirected graph, the one which I have shown you just now, right? So in an undirected weighted graph, it should be a connected one. You're not supposed to leave any node in a dazzling way, right? So the minimum, the sum of the weights of the edges should be minimum. Such a spanning tree is known as a minimum spanning tree. Okay, so a graph can have any number of minimum spanning trees. That means the collection of edges to construct a spanning tree may yield the same minimum value, right? So you can have that. You can find that scenarios also, right? Next, let's look at the properties of spanning trees. Basic spanning tree. Okay, a connected graph can have more than one spanning tree, right? So all possible spanning trees have same number of edges and vertices, right? So first point is the number of vertices. We are not going to lose any vertex or a node, right? As it is connected. The first and foremost point itself that I said is they are connected, right? So we are not going to lose any vertex, and the edges, if there are n minus 1 edges, you are going to have, right? Yes. They do not have cycles or loops. Loops will not be there. So it may be a self loop or any kind of loop. Loops will not be there in spanning trees. Means more than one path between two nodes. There are two nodes. You are not supposed to have parallel edges or a loop. Both are not permitted. Okay. So removing an edge from this spanning tree will make it as disconnected one, right? So it should be minimally connected, right? The last thing, adding at least one edge to a spanning tree will make a circuit or a loop, right? So it is a tree which comes out of a graph in such a way that if you add at least one edge to that, it will no longer be a spanning tree. A loop or a circuit will be framed. Okay, so such a tree is a spanning tree, and it is maximally acyclic. Okay, so few more properties. So in a complete undirected graph, the maximum of n power n minus 2 number of spanning trees you can have. This is a very important point, guys. Based upon this point, a number of questions I have seen in GATE, right? All these, the properties of spanning trees are very important in GATE point of view or any interview placement point of view also. Okay, so please do remember the properties of spanning trees. So here n tells you about n is the number of nodes or number of vertices, you can see. So how many maximum number of spanning trees you can frame out of a given graph is n to the power of n minus 2, where n is the number of nodes in your graph. Then how many number of edges you will have? As I said, n minus 1, where n is the number of nodes. If n is the node, n minus 1 will be the number of edges. So from a complete graph, by removing maximum of these many edges from a fully completely connected graph, if you a maximum of e minus n plus 1 edges must be removed to construct a spanning tree. So what is e is number of edges. Number of edges. So please remember these fundas. These are the basic fundas which you have to remember while working with spanning trees. Okay? Yes. Then where we use these spanning trees? So I hope you know everything we don't learn theoretically. We need to relate it to some physical things or physical point of view. If you think of, then you can map them and you can understand them easily. Let's see at the applications of spanning trees, which they are used basically for the designing of networks. Computer networks, CSE background students will understand it pretty easily, and remaining also communication students also, right? So in transportation, each and every way you can understand network whenever you are trying to connect people or connect nodes or connect places. Everywhere you are going to draw a path between them, and a collection of these paths and everything is nothing but a graph. And with every graph, you can get a spanning tree out of it, right? So civil network planning, cluster analysis. Cluster analysis is the major area which is mostly heard in research and development areas. So where we are going to talk about clusters. Cluster is nothing but a collection or a group of things which share a similar property, at least a single property they share. If pebbles are there, if the each and every, the dimension of each and every pebble will be unique in itself. You cannot relate them. But if they have the same color, you can, based upon the name of the color, you can make a cluster of them, right? Such a thing is nothing but a cluster. In cluster analysis, we use these spanning trees, right? Coming to NP hard problems. So best example is traveling salesperson problem, where a person wants to travel cities or towns. He wants to connect them. He is supposed to visit those cities and towns, but he wants to visit them only once. He don't want to revisit any station, or you don't want to revisit any city or town twice. So in such cases, spanning trees are going to help him, right? So these are the few applications of spanning trees. As I said, what is a minimum spanning tree, or it is also known as minimum weighted spanning tree, because minimum spanning trees deal with the undirected weighted graphs. So even if you add the word weight in it, it's okay. Even if you delete it, minimum spanning tree itself tells you about the hidden fact is that it is talking about weighted graphs. Okay, it is a graph, or it is a variant of spanning trees. Okay, as I told you, weighted, connected, and undirected are the three key fundas of our minimum spanning tree. And when you add the weights on the final spanning tree, that is minimum spanning tree, it should be the minimum one. Okay, then how on what basis, what are the algorithms, prominently known algorithms To construct minimum spanning tree are greedy algorithms. The two greedy algorithms, one is Kruskals and the other is Prims. Then what do you mean by greedy algorithm? It is used in optimization problems. Then why we optimize things, right? So there will be cases or scenarios where you don't want the minimum value nor the maximum value. You need an optimum value which is sufficient to represent a lot. For example, if there is a section of 60 students, if the head of the department wants a review on that section, is he going to call randomly one person out of that 60 and ask him about how were the sessions, did he understand or not? Okay? Or is he going to collectively ask all the 60 members one by one to get a feedback? Right? So, to overcome that, class representatives, CRs का एक फंडा होता है, where 2 or 3 or 4, max 4 to 5 students will be there. They will be selected based upon their marks. It's not that the one who is very good at scoring is very active person also. That will be a rare combination, right? So these are, say, a group of 5 students. So they will be selected based upon the one who is attentive in the classes and the one who is having a good score or percentage in his academics, and the one who is regularly attending to classes, that is attendance is high, right? Overall performance, as I said, overall performance, the 5 people who are having overall performance is going to call, the HOD is going to call these 5 people, okay, and he's going to ask his queries, right? So these 5 people are an optimal solution. I know this is a very blunt example, but for your understanding purpose, I've used this example. Okay, so this is an optimal set which represents the remaining 55 students, right? So they are going to tell a person who is very good at academics, generally he can tell ki the faculty who are teaching are up to the mark or not. No, I'm not saying that student is going to judge a faculty, but he, from his point of view, when when a student talks, we need to even understand that being a faculty, right? Ki उसे समझ में आ रहा है कि नहीं, is able to understand, follow it or not, right? So in that point of view, the one who is having highest attendance will be saying, yeah, are they promptly coming to the classes, every faculty? In that way, it is, guys, don't take it in a negative way. It is a positive analysis which a HOD is going to do, right? So in this way, these 5 optimal set of students, are going to represent the whole set or the section. So that is nothing but optimization. I hope you might have seen SWAM intelligence. You know about SWAM intelligence? Group intelligence, right? So that is one of the optimization problems. So for that, greedy algorithms will be used in optimization. So why we call them as greedy algorithms, ma'am? So Kruskals and Prims are the best examples for greedy algorithms. Why I call them greedy, you will understand soon when I explain you these algorithms. Have a look at this graph. This is a graph with 4 nodes or 4 vertices. They are connected with their corresponding weights. So the weight between say C and D is 1. That can be any unit, as I said. It can be kilometer, it can be anything. Okay, B and D is 6. You can see it is an undirected. I have not given any directions. So if the weight between B and D is 6, from D and B is also 6, the same value. It is not going to change. Okay, so this is an undirected weighted graph. And here is a spanning tree of the same. So have a look at this one. All the nodes A, B, C, D are connected. If you add their weights, which is 11 plus 8 plus 6, which is 25, is the cost of this spanning tree. I'm clearly saying it is just the cost. I have not used the word minimum cost, right? Wait, I'll tell you why. So let's understand this spanning tree. When we were learning the properties, what did I tell you? If we add at least one edge, it will become a non-spanning tree, right? It will no longer be a spanning tree. For example, if I add A and the edge between C and B, which is bearing a weight 7. So you can see that a cycle is formed, right? So now this is no longer a spanning tree. What if I add CD, this edge? So if I start from A, C, D, B and again to A cycle is formed or not? So even adding one edge to a spanning tree, it will make it a cyclic one. And then it will no longer be a spanning tree. Come back to our minimum spanning tree concept. So the weight is, or the cost is, total cost is 25. So is it the minimum cost? Can't you have any other spanning tree which is having a minimum cost? Have a look at this one. I started traveling from A. So I went to B, B to D, D to C. What are the weights? 8 plus 1 plus 6, which is 15. You can see that 15 is far lesser than 25. Now you can say that this is the minimum spanning tree which I have framed. Yes, both are spanning trees, no doubt in it. But the first one is just a spanning tree, whereas the second one is minimum spanning tree. So try with the remaining combinations. Guys, don't create new edges and introduce new weights. We have to use whatever that is provided in the given graph, right? The way, whether it may be weight, edge, vertex, anything. Only within our boundaries, we need to construct a minimum spanning tree. So this is the basic, this scenario shows you the basic difference between a spanning tree and a minimum spanning tree. Okay, so let's look at the first greedy algorithm, which is Kruskal's algorithm. Kruskal's algorithm is a greedy algorithm to construct a minimum spanning tree. This here I have highlighted the 4 steps which are the bits and pieces of the algorithm, right? The first one. The first and foremost thing which you need to consider is remove the self loops and parallel edges. Which edge you are going to remove is the primary concern. Remove the parallel edge which is of higher weight. Why? My task is to construct a minimum spanning tree, not a maximum one, right? And I have to reduce the cost, right? If I want to reduce the cost, I have to remove the parallel edge which is bearing higher weight. Have a look at this graph. So between A and B, I have 2 edges, right? One edge is having a weight 6 and the other is having 9. Okay, so these 2 edges are known as parallel edges. Now, if you want to construct a minimum spanning tree for this one, first and foremost thing is you have to remove this one, 9, because it is overweight. Okay, so remove that. Next, as I said, remove self loops. Self loops mean have a look at the node C. It is having an edge to itself, right? This edge whose weight is 1, here it's starting, the node starts at C, the edge, basically the edge starts at C and ends at C, right? The source and destiny are the same. Such a thing is a self loop. Remove them. There is no use of them in our work, right? Our funda is to have minimum weight and construct a spanning tree. right? Right. Now, once you remove loops and parallel edges of higher weight, sort all edges in a non-descending order of their weights. That is ascending order. Means you need to construct a table. You need to construct a table. And this table will have 3 columns. One will be bearing weight. Second one will be the source vertex. Next, third one will be bearing the destination vertex. Right? Source and destination vertex. Or you can say head and tail. Right? For example, if let's consider C and B edge. This is the source and this is the destination. You can also call this is the head, this is the tail. In different books, you will be finding different terminology. Don't get confused, my dears. And how we are going to mark an entry into this table is based upon their weights. Least one enters first. In this one, say weight which I can give an entry is 2, the least one. After removal of 9 and 1, I'm talking about. Okay. Minimum weight is 2 and the source is B and destination is D. Is it mandate to consider B as the starting node or the source map? No, it is not mandate. It is an undirected graph. You can write in either way. Other way as I'll write it for your sake. The source is D and the destination is B. Okay? Happy? Now let's go for the next one. Again, and another 2 I am having weight 2. Source is T and the destination is D. Next is 3. Source is A, destination is C. In this way, you are going to fill the whole table with all the weights. Okay, this is the point of your example of your second step. Once you construct this one, once you construct this table, pick the smallest edge. Okay, check if including that edge will form a cycle or a loop. If it is going to do that, discard that weight. If it is not doing any harm to our job, add it. Add it to the spanning tree, right? And the last step, you have to repeat from step 2 to step 2 and 3 repeatedly unless you get V minus edges. V is the number of nodes. V is number of nodes. Or you can have, say, vertices. Either way you can say. Sorry guys, my handwriting is very bad. Kindly adjust. Okay. The number of nodes or vertices. So we have seen the properties of a spanning tree, right? Even it is minimal spanning tree or not, it is a spanning tree. Then it must abide to the properties of a spanning tree, which says that if there are n number of nodes, then the spanning tree will have n minus number of edges, right? Even minimal spanning tree must abide to this rule. It cannot overlook it. Okay, so you are going to repeat the same to get a minimal spanning tree. This is Kruskal's algorithm. Let me explain you the same with an example. Have a look at this graph. So this is an undirected weighted graph. You can see. So the weights are as given. A, B is 4, AC is 4, BC is 2, CE is 2 and so on. Okay. So what was the first step is to remove parallel edges of higher weight and loops. Here nothing is of that sort is there. So skip step 1. What is step 2? What is step 2? Take a table, mark an entry in an ascending order of their weights. Right. This is the table. So minimum weight is 2 source node is B, destination node is C, right? So mark an entry into it. Now let's start constructing the same. So I have taken on a white sheet all the nodes, only nodes. Now I'm going to add the nodes which are edges which are helpful in the construction of a minimum spanning tree. So the least weight is between C and B. Adding this edge will not violate the rules, that it is not going to generate any cycle or a circuit. So I can add it. Next is between C and E, which is 2, a minimum weight, right? Even adding this edge will not harm me. I have added it. Next, between E and F, which is 3. Even this is not going to harm me. I have added it. Next, between D and F, which is 3, I have added it. You might get a doubt. In the table, if the entries are 2, B, C, 2, C, E, 3, D, F, 3, E, F, and so on, what will be the situation? Yes, this can happen. The first entry will be least one, BC, which is 2. No problem. No circuit is formed. Between C and E, 2. No circuit is formed. Then between D and F, add this one. Even though it is not connected, add it. Not a problem. Right? D and F, happy. Then talk about E and F. Adding this, is it going to create any circuit? No harm in that. Add it. Even in this order also you can do. It is not mandate that the order in it must be in a chronological way or not. See, here I am using AB's alphabets, or I can use the names of the nodes as numericals 1, 2, 3, 4 karke. But in real life, will you have the same? If you are talking about cities, so we cannot go for it, right? So many cities, the first letters will be the same, right? So even if you want to consider the first letter of the city, even that will not be possible. So it is not in that way as that you are thinking that you need to go in a connected way. It is not required. Just follow the blunt rule. Minimum, add an edge with a minimum weight such that it does not form any circuit. If it forms, remove it or discard it. Next is between A and C, which is 4. Have a look at this tree right now. How many nodes it is having? Number of nodes is equal to 6. How many edges it is having? 1, 2, 3, 4 and 5. So what our Kruskals algorithm was telling? It was telling that if you have V minus 1 edges in your spanning tree, then the job is done. Am I right? So here the value of V, you can call it as V or N, is 6. The edges is 5. Job done. Right? This is your minimum spanning tree by using Kruskals method. Then what is the cost of it? Add all the weights on the final spanning tree, which is 2 plus 2 plus 3 plus 3 plus 4, which is 14. I hope you understood Kruskals. Let me explain you with one more example. This is a bit higher one, which is having 9 nodes. Make a note of this diagram, please. Make a note of this graph, more specifically if I talk. Please make a note of this one with the edge weights. Right? You can see you can see many circuits are there from 1 to 7 to 8 to 2 1 again. One circuit is there. Many circuits are there, right? We need to break them all to get a minimum spanning tree, right? I hope you might have written it or taken a snapshot of it. Fine. What is the second step? To construct a table. As my graph is not having any loops or parallel edges to remove, I can directly go to step 2, where I'm going to construct a table. Have a look at this one. This is the table which I have constructed, right? So weights are in the ascending order from 1 to the maximum weight, which is 14, between 3 and 5, nodes 3 and 5. As I already told you, the names of the nodes can be alphabets or numericals also. So I have intentionally changed it in numericals. So I will draw on the table in ascending order. If you are done with it, let's go for this construction. So on a plain chart, I have taken all the nodes, only the nodes, without any edge. Without any edge. Okay. So you can start with any node of your wish. First of all, in Kruskals, we are going to start by adding an edge with minimum weight. What is the edge with minimum weight? The edge between 7 and 6 bearing a weight 1. Always think, by adding this edge, is it going to form a circuit or not? It is not going to form any circuit. This is the first edge, bhaiya. No problem. Add it. Next, go to the next one. Next edge, which is not going to frame any circuit form, any circuit, which is 2. Between 6 and 5. 2. Then, it did not form any circuit. The next one. And another 2 between 2 and 8. I hope you can see that. The edge which I have added just now is no way related to this one. Right? The previously added edges. These two act as subgraphs of the given graph. Right? But they are not spanning trees, my dear. Next least weight edge, which is not going to form any cycle, is 4, between 0 and 1. Between 0 and 1. Then next least one is between 2 and 5, which is 4 once again. Even adding this one will not harm. Next, between 2 and 3, which is 7. Between 2 and 3, which is 7. Next, between 1 and 2, which is 8. Right? Then between 3 and 4, which is 9. Have a look at the number of nodes, which is 9. The number of edges, you need to have a watch on the number of edges always. Okay, so 1, 2, 3, 4, 5, 6, 7, and 8. Right? So, our basic requirement, which is if a graph is having n number of nodes, then the number of edges will be 1 less than the number of nodes, which is achieved. Right? So, this is the final minimum spanning tree which you are going to get when we use Kruskal's algorithm. Okay, then yeah, this is the spanning tree. Then what about the minimum cost? Add the weights on the edges. When you add all the weights, that is 1 plus 2 plus 2 plus 2 4s plus 1 7, 8 and 9, you are going to get 37. This is the minimum weight that you are going to get when we apply Kruskal's algorithm on a given graph. Remember guys, The number of steps that we have are, first and foremost one is to remove parallel edges, the parallel edges and loops, or you can even call it a self loop. Second one is to construct a table in the ascending order of the weights. Then third one is to add edges. We are going to add edges in such a way that they do not form any circuit. Okay, so in this one, if I add this edge, will it, if its weight is the same 9, even if I do that, it is forming a cycle, my dears. I cannot add it. Even if its weight is 1 also, I cannot add it. What if I add an edge, something like this? It is having a weight 6. I hope you remember the graph. It is much lesser than the weight is much lesser than the 7. That is the edge between 2, 3, between 1, 2, and between 3, 4. It is much lesser weight. But if I add it, that is, it is going to form a circuit. If it forms a circuit, then even if it is having the least weight, we cannot add it, because you will not get a spanning tree. It will, minimum ki baat chodo yaar, it will not be a spanning tree in itself. Okay, so these are the 3 steps which you need to follow to construct a minimum spanning tree using Kruskals method. As I already told you, this method is highly useful, this greedy method. As I hope you understood why I call this as a greedy method. See how choosy it is. It is selecting, it is starting from the least weight or least weighted edge to construct a spanning tree. And in each and every step, when it is adding, it is looking whether by adding that edge, am I going to get a profit or not? Right? If it gets the profit, that is, it is adding a minimum weighted edge, but circuit is not formed. It's the way it is working is a greedy way. That is a simple definition I can give. If it is too choosy about selecting the edges based upon a criteria, it comes under greedy methods. Thereby, Kruskal's method is also known as a greedy method. Okay, so these methods, Kruskal's methods, can be used for traveling salesman problems, solving that, and any cluster analysis, any networks. You can consider any discipline of engineering or sciences. Your Kruskal's method will be one of the best methods, and we are going to learn in the analysis part to when you try to analyze clusters of data, right? When you try to find similarity in the data, right? So this is the purpose of Kruskal's algorithm, and this is how it's executed. I hope I have explained you with 2 examples. If you still have any queries, please do post me. Okay, and thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.